We're going to do 4 problems from the text. I assigned these for homework, and students had difficulty with these questions, so let's look at them together now. Problem number 21 in section 3.2 really is one of the fundamental differences between finite sets and infinite sets. Suppose you have a set. Notice he doesn't say infinite or finite. You have a set. If you remove some things from the set, will the collection of remaining things always contain fewer items than did the original set? Well, certainly, if the set is finite, if you take elements out of the set, you have fewer left. We've known this since we were babies. But it's not true necessarily in the infinite case. So the answer is no, not always. So let's demonstrate with an example. If we have, well, let's take our favorite infinite set, the natural numbers. If we start with n, the set of natural numbers, we could remove, for example, remove the evens. And then what are we left with? Left with, well, the set of odds. 1, 3, 5, 7, 9, and so on. So we took out actually infinitely many numbers. We took out all the evens and we're left with the odds. But certainly there's a one-to-one correspondence between the natural numbers and the odd numbers. For example, we could just use the fact that we can list them and say, well, let's let 1 correspond to the first on the list, and 2 to the second, and 3 to the third, and so on. You see, we have a natural one-to-one correspondence set up by the list itself, the fact that we can list the set of odd numbers. How about another example? Let's remove this set of numbers 1, 2, 3 up to 10,000. So we're taking out 10,000 numbers, but then we are left with, well, 10,001, 10,002, 10,003, and so on. Again, an infinite set that can be listed. In fact, that's the notation we use to write the elements that are left. 1 could correspond to the first one, 2, 3, and so on. The set that is left after removing 10,000 of its elements is a set which is still in one-to-one correspondence with the natural numbers. So there are not fewer elements in these 2 examples. There are not fewer elements left in the remaining set, even though we removed elements from the natural numbers. Now, question 22 asks us to find a set that we could remove from the set of natural numbers so that the set of remaining numbers does contain fewer numbers than the set of natural numbers. Well, in other words, we want to remove elements in a way, or remove numbers in a way that will leave a finite set remaining. And, well, let's just take out, remove this set of numbers. Let's remove 101, 102, 103, and everything after that. So remove all numbers greater than 100, and we are left with a finite set. 1, 2, 3, and all numbers up to 100. So the cardinality of this set is equal to 100, which is certainly less than the cardinality of the natural numbers, which is an infinite cardinality, one that we called Aleph naught. But notice we had to remove infinitely many numbers, but we had to remove them in a certain way to leave a finite set remaining. Number 24, suppose we have two sets, and let's take an example. Let's take our two sets will be the natural numbers and the integers. Let's take those two sets. And we are able to pair elements from one set with elements from the other set in such a way that all the elements from the first set are paired with elements from the second set. Well, I could do that by just listing part of the integers. Like let's start at, we did this in class, I think. Let's start with -3, -2, -1, 0, 1, 2, 3, 4, and so on. There's a list of integers, and whenever I make a list, an infinite list, I have set up a correspondence with all of the natural numbers. 3 corresponds to 1, -3, -2 corresponds to 2, the second one on the list. The third number on the list, -1, would correspond to 3, 0 to 4, 5, 6, 7, 8, and so on. Whenever you list an infinite set, you create, in doing so, a natural one-to-one correspondence with the natural numbers. So we see here that all of the natural numbers are paired with one integer, but there are integers that are left out of this pairing. And let's see, what are they? Well, -4, -5, -6, and all numbers less than that are all left out. So this is a correspondence between the natural numbers and the integers, but it's not a one-to-one correspondence. The question asks us, does this mean that the two sets do not have the same cardinality? And the answer is no, it doesn't mean that at all. It means that this is a correspondence that is not one-to-one. Remember, this is the definition of two sets having the same cardinality. Two sets have the same cardinality if there exists a one-to-one correspondence between the two sets. Just because there are many, many correspondences that are not one-to-one, it means nothing. What we're concerned about is, does there exist a correspondence that works? And we know in the case of the integers that there certainly does. How about this list right here? 0, 1, -1, 2, -2, 3, -3, etc. Here is an infinite list, a one-to-one, natural one-to-one correspondence with the natural numbers, and every integer is on that list exactly one time. So every integer is paired with a natural number, and every natural number is paired with an integer. In this way, 1, well, let's see, change color. 1 is matched to 0, 2, 3, 4, 5 is matched to the 5th on the list, 6th is matched to the 6th number on the list, 7, etc. Problem 25, the last one that I'll do on this video, sounds very much like 24, but if you read it carefully, you see it is not. Suppose we have two sets, and here's the word that's so different. Every pairing of elements from one set with elements from the other set results in having elements from the second set never paired. Do these pairings imply that the two sets do not have the same cardinality? Yes, because if every pairing fails, that means that there does not exist a one-to-one correspondence. So your answer is yes, since every correspondence fails to be one-to-one, there does not exist a one-to-one correspondence. That means the two sets have different cardinalities. Okay, so think carefully about these problems. They really are the essence of what we are trying to learn in section 3.1.